Hey everybody, welcome back to acid acidic buffer calculations part 2. Okay, so in this video what I'm going to do is I'm going to show you, I'm going to take that same acidic buffer that I used in that last calculation, in that last part 1. And what I'm going to do now is I'm going to add HCl to it. I'm going to add some hydrochloric acid. We're going to see what happens to this buffer system as I add hydrochloric acid. And this is really where buffers become powerful, because what the buffer is going to do is it's going to attempt to keep the pH relatively constant. Now, it can't keep it exactly the same, but it actually keeps a system relatively close to the same pH throughout the buffer system's duration. Okay, so I'm going to start with the buffer system. I'm going to set that all up, and then we'll talk about it. Okay, the first thing I'm doing here is I'm looking at the major species. So I'm looking at what do I have in the solution. So I'm going through and analyzing what I have. I have a weak acid. So we go ahead and write that down here. So I have weak acid. Okay. I have that conjugate acid from a base, the strong base. It's sodium. We get rid of it, right? We cross off those sodium ions. Now what I have here is I have that conjugate base of a weak acid, and I right away recognize that as my buffer system. So that's my buffer. Okay, there's my buffer. Water, it's going to have an effect. Again, it's going to react with things. It's really more effective when just the conjugate base is left over, but we'll keep it here. This is a strong acid. Whenever we have the hydrogen ions or hydroxide ions by themselves, we have strong acids and strong bases, and we got to keep in mind that that's going to have an effect here. And then chloride ions, same thing as the sodium. We get rid of them. Chlorides, bromides, iodides, those anions that come from the strong acids like HCl, HBr, HNO3 are going to have no effects, and we ignore them. Okay? So what I have here is I have the buffer system and the strong acid. Now right away, what I should notice is that I have my strong acid and a base are going to react together. So there's going to be a reaction between these two first. Then after those two react, we can then let our buffer system come back to equilibrium. So whenever you have strong acids and strong bases in here, there is no equilibrium. So what I'm going to do is I'm going to start with just a traditional Bca table that we did in the first half of this semester. Okay, so I'll set that up and then we'll take a look at it. Okay, so to start off with, I created the reaction between the strong acid and the conjugate base, which is going to produce more of the weak acid. Now, one thing I forgot to do when I wrote the problem was I forgot to put the volume of the buffer, because if you notice when we use the Bca tables, we should always be using moles when we use those tables. So we should be putting moles into our Bca tables. So I had the moles of the acid, which they gave me here in the problem. What I didn't have was the moles of the conjugate base and the weak acid. So I had molarity, so what I needed was volume. So I realized I made the mistake and forgot to add this. So if I have 1 liter of the buffer and I take 1 liter of this molar solution, I'm going to end up with 0.1 moles and 0.1 moles. You can just do a volume times molarity, pretty simple because you're multiplying by 1, and you would end up with 0.1 moles. All right, so I'm doing a traditional Bca table, just like we did before. So when we deal with Bca tables, one of these has to go to 0. One of them has to be limiting reactants when we have a Bca table. It's because the strong acid is just flooding the system. There's just tons of those ions in there, and they keep going into the solution until they just run out or something else runs out. In this case, the strong acid will run out, and this will be left behind. And what I'll have left over is 0.080 moles of the conjugate base, and I'll have on this side 0.120 moles of the weak acid. Okay, so notice what's happening here. As I add this acid, the conjugate base is going down. I'm losing conjugate base, and I am gaining weak acid. And that's what's going to keep happening as I add more and more of this acid. More acid, less base, more of the conjugate or the acid in this case. I guess the conjugate base would go away. Again, conjugates depends on the manner how you refer to those, but because these are just the conjugate pairs. So the base goes away, the weak acid comes in. All right. Now what I'm going to do is I'm going to take the results of this, I'm going to convert it back to concentrations, and then what I'm going to do is I'm going to go ahead and add back the equilibrium, because notice this is gone now. Okay, so we're going to take a look at stage 2 of this reaction. Okay, so if I analyze this reaction at the end of that last step, at the after part of the Bca table, I still had some of the weak acid. Well, again, I don't really care about the sodium ions. If you want to keep them in the reactions, it's up to you, but I like to drop them out. I had some of the conjugate base that was left over. okay, that was still remaining. The water, it's always going to be there. This was gone. This was used up. Remember, this went to 0 at the end of it, so I no longer have strong acid, and this has no effect, right? So the chloride and the sodium have no effect, and this gets used up at the end of the Bca table. So now what it becomes at this point is just the same thing we did in that last video at the very end, where I now have just the buffer, where I just have the weak acid and a conjugate base. So now I'm going to write that out just like I did in part C of the first video that we did with calculations in part A. So let's take a look. Okay, so I set up the ice table, and what I did was, in this case, I didn't put water in here. If you go back and you look at part C in the acidic buffer calculations part 1, I had water in the reaction. I purposely left it out just so you can see the comparison of having a hydronium and hydrogen ions without having that extra water in there. Okay, so you can compare and contrast this if you need to. Alright, so notice what I did was I took the outcome of the Bca table, the after part. I converted these things to molarities, and it happened to be the same number, again, because my volume was 1 liter. Just watch that, because your volume isn't always going to be 1 liter. It just happens to be this way so that I can do the calculation simple for you. Alright, so I took the after part of that part and made it the initial of my ice table. And I kept this in here because now notice this went down, this went up. Okay? I'm going to go ahead and finish the ice table just like I normally do. Okay, so I've completed the ice table and plugged everything into the Ka expression and simplified and solved for x, which I did over here. So here's my value of x, which is 1.9 times 10 to the minus 5 molar. And I put molarity here because it is a hydrogen concentration. Take the negative log of that, and I end up with a pH of 4.71. Now, if you go back to part C of the acidic buffer calculations in the last video, the last one I did, the pH for that one ended up being 4.89 if I'm not mistaken. So 4.89. Now, by adding the strong acid, the pH didn't change that much. Okay, it stayed relatively the same. So again, same pattern. Once I get to the ice table, it's the same thing we've been doing. We're just plugging in the new numbers and then following the same pattern over and over and over. There's a lot of repetition here. Like I said before, I think the hardest part is getting from here to here. That's the biggest mystery. One last thing I want to show you is what happens if I didn't have the buffer. What if I took out this portion here and all I had was just the strong acid? What if I don't have a buffer, but what I did was I just add 0.02 moles of hydrochloric acid to the water? And I'm going to show you that real quick. Okay, so the major species that I have, if I drop out the buffer, are just the hydrogen ion, the chloride ion, and the water. Remember, chloride ions don't do anything, so really, remember, a strong acid, whatever the concentration of the strong acid is going to be the concentration of the hydrogen ion. So in this case, my hydrogen concentration is going to be the 0.020 moles over the 1 liter, which just comes out to 0.020 molar. Well, if that's the concentration of hydrogen ion, I can just quickly plug that into pH, and my pH is going to come out to be 1.70. So the reason I'm bringing this up and showing you that this is what happens to the pH if I put the acid in there by itself with no buffer. But if I put it in there with the buffer, my pH doesn't drop down to 1.7. It actually goes to 4.71. So it maintains that pH. It keeps the pH from plummeting or the pH going drastically high. You could follow the same pattern just plugging in OH, right? You could do a sodium hydroxide here, and instead of the pH going drastically up, it's going to still maintain and stay at this level. We'll look at some of those calculations in class and do a lot of practice problems with this. But please spend the time on the buffers, because the more time you put on buffers, the easier the titrations will be. All right, guys, I'll see you later.